Okay, good afternoon, everyone. I'm Richárd Forster. I'm working as a PhD student at CERN, working on graph visualization in a project called Collaboration Spotting, and you will see what kind of computations we are using. I will make a short summary about them, and then you will see what kind of networks we are trying to use to improve the visualization of our graphs. So now I will change to my presentation. Okay, so now you should be able to see it. So the presentation is about watch regeneration with art for efficient graph visualization. So as I mentioned, in short, I will go through what's in for regeneration and what kind of computations we are using. For example, community detection and force plus for making the nodes visualizable. And then I will go to the trigger with the RNN, how it works and what we achieved with it, and then some short outliers for future work. So the graph generation. This is a process that we require to do for every single graph for every user. Whenever someone makes a search, we will have to get back the data from the database first, of course. But it is not enough to have the data, we also have to make some pre-processing, as we will need to have collaborations based on the data that we have received. And from there we will see what kind of nodes and edges the database have returned for us that we would like to visualize. So for example, here you can see graphs. Each of them is a search for technology. For silicon, one is for database, one for 3D technologies, and one for CT-related technologies. And you can see at the bottom that, for example, the database has 17,000 nodes, the silicon 25,000, 3D 35,000, and CT was 53,000. And here at the top table, you can see some performance numbers, how much time it took to compute the collaborations, the node, the edges. So you can see that as long as we have many edges, the time for edge generation takes a bit longer, but for the collaborations, for example, it's not so easy because the collaborations will also depend on the type of the graph, what kind of connections they have, and how many connections one node will have to the other. So it's basically what the collaboration means is that in the case of a paper, for example, is how institutions are working on that paper, how many authors it will have. So as you can see, it differs because different papers can have different number of authors and as such different number of institutions. So let's go to community. What that means, we would like to have an information about the communities, the groups that are working together in a given technology. And this is very good in real-world data, as you can see, cliques that are working together that tend to have more similar research projects and similar topics. To generate this, we are using the Luban methods. That is a modularity-based community detection, where modularity means that based on the nodes, their connections, based on the degree of the node and the weight of the edges, we are getting a number that can be used as a qualifies the communities, and based on that we can decide what kind of movements we would like to see in the nodes. I will not go into deep details because this is not the main part of the presentation, so I will just show some performance numbers later. So as I said, the Luban method is a multi-phase iterative greedy algorithm. That means that we are building a tree, a dendrogram, that each layer will contain the nodes that are moved into a different community, and as you go deeper and deeper, at the leaf side you will see the original nodes, but inside the tree you will see the communities, and the top will naturally, the root will contain the whole graph. This is monotonically increasing, which means that we are getting new communities based on the increase of the modularity. So we will try to see better results in each iteration, and we will not try to go back. This is basically a sequential algorithm, but based on analytics, we were able to parallelize it. And so performance numbers, as you can see, these are the same graphs that I have shown before for the graph generation. And there you can see that, for example, CT graph, it is the biggest with 53,000 nodes and 325,000 digits. The computation on GPUs took only 1.4 seconds for the community detection, while the CPU took more than 12 the time of that computation. So we were able to achieve quite a lot of performance improvement there. So what happens with our communities, we will see some very colorful graphs where each color represents one community. So you can see, for example, that the Medipix related technologies are handled in red. Those are connected together and they are belonging to the same community. And the same is true for the rest, that each color will represent one community. What happens after we achieve the collaboration, the communities? To be able to visualize the graph, we will have to do something that makes it understandable for the end user. So the reason why we are using forced class is because it is a force-directed layout algorithm that is basically an n-body simulation. What this means is that the nodes themselves will try to repulse each other as they are getting closer and closer. And those that are connected with an edge will also attract each other based on the weight of the edge. This makes the visual interpretation easier, as you will not just have a bunch of nodes around the screen, but they will have some intricate meaning behind that. And of course, based on the starting state, the end result of the force-directed layout can be different because the repulsion and the attraction will handle them differently. So performance numbers for the same graphs that we had before. We can see that also on the biggest graph, the performance improvement is the greatest. Compared to the CPU and GPU, we were able to achieve a 9.8 times faster computation time. So for surplus layout types, on the left side you can see the original layouts. As you can see, it's still not very meaningful, while it's still better than just nodes hanging around all around the screen. At least they are organized in a nice circle shape. But on the right side, you can see a community-based layout, which means that we have first computed the communities. As you can see, you will see the colors, and each color, each node of the same color are in the same place. So the communities, the nodes belonging to the same communities are together, and these communities were used to generate a force surplus layout. So this means that we have generated the layout for each community. And after the communities were covered, we have took their nodes and built a new graph that contained all communities. And based on that, we have generated the force surplus layout again, and at the end, we have just replaced the original nodes, and yes, we have received this nice looking graph where you can definitely see the different communities and how they are organized around the screen. So, because the force surplus layout is an n-body simulation, it also has some performance problems because as an n-body simulation, the original implementation is an n-square computational intensive algorithm. So you will need to compute each node with, you will have to compare each node with each node to get the proper attraction and repulsion forces, and then you will have to also apply it to each node. To avoid this, bar side tree can be used to increase the performance of the algorithm, as this algorithm allows you in a 2D plane to segment the space, so you will have different regions, and the process is that you will halve the space until you only have one node per region. We will see an example for that later. So we would like to use RNNs, recurrent neural networks, to improve this process. And for RNNs, it means that we are having a neural network that not only has the input state of the current time step, but we also have the output of the previous time steps. So this way we can understand sequences that has an inherent meaning based on past experiences. By default, the RNNs are not so good because they have some problems with vanishing gradient. That means that based on the error, the gradient of the error can also decrease the learning rate quite heavily. And this means that you will stop training the network before any reasonable results could be found. So to avoid this, we can use long short-term memory cells that while still have some possibility that they will have this vanishing gradient problem, they are still much better in understanding sequences and understanding the connection in the data in the sequence. So for a very short, small example for a Balsa tree, you can see in the top left image, basically this will be our graph, and here it is separated into different regions. And you can see that one region only has one node. And at the bottom, you can see that this will be a quadratic tree where each node in a graph that is not a leaf will be a region, and each leaf will be a node in the original graph. And what we would like to see is how to compute these trees based on RNN networks. So what we had is, took the data, generate quadratic trees, and then what we have generated, we have took it and modified it a little bit to be a perfect input for an RNN. So we have transformed the Balsa tree result into a time series, which means that each node have became one. What you will see is that sorry. Okay, so each node will come in one time step, which means that at the beginning you have only one node, that in the next time step there will be another node, and so on. So in the input sequence, we had the first variable representing the time step, then we will have the coordinates, and then we had the result of the previous generation, which in the beginning is always initially -1, so we will know that those are extremal elements because we will not have a community that has we will not have a region that has an ID of -1. And then at the second part, we will have the new generated numbers of the regions. And we have generated a model trained on 1,000 nodes, and we were able to achieve 94% accuracy, which means that sometimes it can happen that the nodes are put into regions. Multiple nodes can put into the same region, so it will not always satisfy the requirement that one node per one region will be available. Sometimes it can happen that they are pushed to the same. But in 94% of the cases, the generated Balsa trees were the same that we had generated in the normal original Balsa algorithm. So how to use this to increase the visual experience? Originally, we had a graph that the communities detected. We have a force-plus layout applied to it, so we can see what kind of communities we have. We have seen the nodes connecting to one community based on the colors. But what happens if we would like to make some analyzation? In this case, the graph is quite simple. There's not too much nodes. The connections are not too dense. You can basically say all the nodes, all the labels, no problem with that. But what will happen if that will be a much higher amount of nodes with much higher density? So on the right side, you can see only the communities, which means that we have took from the left-hand side the nodes belonging to the blue community and replace them with a blue node that represents the same size that they will have together. So in this case, if we will generate the force-plus layout based on this, we will be able to get this layout at the end if we will replace the original nodes as I mentioned before, with the community-based Forster plus layout generation. So we have the community graph at the beginning, and then we apply the bar search tree generation, so we will have the regions on them. So you can see that every region belongs to one node, and one region has only one node. Here in this case, with the pink nodes, you can see that it has some parts that are hovering over the neighboring regions. But the region that has the biggest part of the node will be the region selected for that node. So this node belongs only for this region above the red nodes. So let's say that we would like to analyze the Medipix node, that is the red one. And let's say that what we would like to do is get our nodes that are important to us and put them into a different space. So in this case, we will put them into the top right corner of the screen. In this way, we will have the graph in the original position, but we will have some nodes, some communities, and later the nodes belonging to those communities that are separated and much more easily visible. So first, this is for generating the training data set. So first, the node was in this region below the pink one. Then by hand, I was moving it to the other position where the region had became the other one between the yellow and the pink node. And this time I regenerated the bar search tree, and the result of the bar search tree was stored for the training input, and it was transformed, so it will have a time step, it will have the coordinates, and it will have all the other variables that was mentioned before. So then the red node is advancing again, now it's in the top region. And at the end, the red node advancing to the final position in the top right corner. This means that we had 3 time steps. In the 3 time steps, we had generated a new bar search tree. The new bar search tree output was used as input for our training. And then we have used those 3 data sets to generate a new model that is not really generating the original bar search tree, but it tries to generate a bar search tree that will position our selected node into the hot zone. So in this case, in the top right corner. So the states are stored for only the Medipix node in this case, because only the Medipix node had been selected and only that one was moved. So in this case, our model will be able to only position the Medipix nodes. And so this model will move the node through the same regions, as I was pushing the node from one region to the other, and I was registering that information as a training set, as a part of the training set. It will make the model reproduce it later on, but when it tries to get the next state and the next time step, it will push the node, and we will be able to see that the same node is moving in the same position, the same nodes as I was doing by hand. So in this case, we have a preprocessed graph that is based on the Medipix and the MPGD algorithm. So we have decided to, in this case, move 2 nodes. They were on the bottom left corner from the pink nodes. Now both of us are in the top right in the hot zone. So in this case, we can easily see what nodes are connected to the community, and those communities are separated from the big graph. So we will have a much more better understanding of what it is. So it is the original graph on the left-hand side. You can see that the Medipix red nodes are still inside. The yellow MPGD is still inside. And on the right-hand side, you can see that they were moved outside. So, of course, this can be done manually too. Why would we need to train a network for that and to do it for us? Well, in this case, this was easy because the graph is small. It can be easily done that we will just select these nodes and move them somewhere else. It's possible. It will be also possible in a much bigger graph, but in the case of a bigger graph with higher density, it might happen that there will be so many nodes that we will not be able to see what we would like to move. So if we will know that we have a graph where, let's say, speaking for medipix, that node will still be present in the graph, but we will not be able to identify it there because there will be so many different nodes in the system. And if you will have so many different nodes, you will also have much more edges, and because of the edges, you will not be able to see the labels, for example, or maybe even the nodes will be hidden. So if we will definitely know that we have a node that we would like to push, and we will have a model for that node that will be able to understand that based on the current region and knows how to generate new regions, and it will know that the final region at the end will have to be somewhere that was pre-selected by the user. So it means that in my case, I was always pushing to the right-hand side, but if you would like to move your nodes to the left-hand side or the right-hand side or somewhere else, you will have to provide user data for that, and if you will retrain the model, it will be able to understand that your initially selected important nodes will have to be positioned in that final state at the end. And because in a much denser graph, it's very easy to see. It's also very easy to select. So if you will have a graph where you don't really see what's stored in the middle of the graph, let's say, you will have a lot of edges. They are hiding the node that you're looking for, but you know it's still there. You can say to the system that you have this node, you understand that this node will have to be pushed somewhere else, that you will know that is important for you, that you will use as your analysis phase. Then you can say that push that node into the right-hand side, or in my case to the top right corner, and you can automatically analyze the system without even selecting any nodes. And then even if in a very complex graph where you will not be able to see too much, but you know that there should be something, then you will be able to generate a new graph based on that complex mass that will be able to tell you what are the connected nodes. So in this case, if we will have medipix in a very big graph, we will be able to see that medipix contains 4 nodes. They are connected to each other and they represent one community. So what we would like to see in the future with this, well, the problem with the current implementation is that I'm using the system alone. I have some graphs generated. I know that I'm only generating a graph that will definitely have a medipix node, for example. And I'm moving it around, I'm generating new regions, I'm pushing it to the final region, and then storing everything, moving into training set, generating it, and training the model. But what happens if multiple users will try to put it into different places? We would like to see what happens with the final result. If multiple people will say that they would like to put it to the same region, then we will see that the model will understand that that region will be an important one. But if, for example, if multiple people are using the system and all of them would like to see different hot zones, then what will happen to the final region? That is very interesting, that we would like to see. If the model will be able to make some generalization based on that, so we will have some automatically computed, if you would like, hot zones in the system that will position important nodes in a complex graph that may have a general appealing to the users. And of course, we would like to, and we will need to test on more complex graphs, because the graphs that I'm using are usually quite simple with only hundreds, maximum a few thousand nodes, where I can still easily see what I would like to use. So even if I am generating a graph, I will always see that medipix node that I would like to push. So it's not very complex in the current test cases. But as it was shown, it is possible to use recurrent neural networks to push one selected important node and push it into a region that will later use for more thorough analysis. And of course, this is just prototypes. This is just in the prototype state. The full system doesn't have this functionality. So we would also like to see if integrating it into the system, how the users will use it, if it will have some real value at the end. Because right now it's very easy to just select nodes and move them around. Even if you are having a very complex graph, you can still zoom zoom in, zoom out, move the surrounding nodes around. You can still find what you would like to show, but to see how it works in the real system. So thank you for your time, and this is the end of my presentation.